Mao here from the University of Michigan, and she's going to talk about dynamics and rheology of generic mechanical networks today. So, Xiaoming, go ahead, thank you.
And this one. Okay, can you all hear me okay? Okay, yeah. Very nice meeting you. It is my great pleasure to come here. I just arrived this morning, so it is really exciting to be here. So let me find a chalk. So here is a brief outline of what I will talk about this week. So today we are going to talk about some basics of dynamics of disordered or ordered networks, and a little bit of rheology, how discrete network mechanics connects to continuum limit rheology, viscoelasticity, these kind of general ideas. And then lecture 2 to 3, we are going to spend a lot of time talking about general introduction to topological mechanics. So I believe you have already heard a lot about topological mechanics from beautiful lectures from Tom last week. So here, what we are going to do is to start from a different perspective. We are going to talk about finite frequency topological edge modes which live in band gaps. And I'm going to do a very general introduction from general ideas of topological states all the way deep into mechanical topological states and specific examples. And after that, in lecture 4, I'm going to show more examples of these and then go more specifically to talk about Maxwell lattice topological states, which are what Tom already introduced. And I'm going to talk about a number of new developments in this field, especially in the direction of disordered Maxwell network topological mechanics. So this is an outline. And today we are going to start from here, where hopefully I will talk about not only statics, but also dynamics of generic mechanical networks. So let's start from the basic equation, which I believe you have all seen earlier this week, where we write elastic energy of a network into this form. So I suppose you have already seen this equation, right? And from, I think, lectures last week, you also have learned that you can construct this so-called dynamical matrix using the compatibility and equilibrium matrix like this, right? Where this C is the compatibility matrix, and this K is the diagonal matrix of the elastic constants. And then this CT, or defined as Q, is the so-called equilibrium matrix. And you can construct the dynamical matrix out of this, right? So I think in general, it is helpful for learning if we know each other better, right? So in order to discuss general dynamical properties of these networks, I would like to start with a little bit of interactive components. So I would like to ask you, when we write an elastic energy like this to describe a real system, what are the assumptions that we have made? What have we left out when we write down this for a real material? So what assumptions we have made? Any ideas? Yes? Sorry, what did you say? Yeah, so this is linear theory or harmonic elastic energy. And these two are saying the same thing, right? We expand the elastic energy to the harmonic level, which means U squared. And then linear refers to when you write the force in response to this elastic energy, it is derivative of this E with respect to U, and we keep linear term. So very good. That's the first assumption. What other assumptions have we made? all the mass. So have we defined, so does mass appear here? This is the potential energy, right? And if you want to include mass, what is the term that you would need to write? It is the kinetic energy, right? So you can write it as Lagrangian equal to T minus V, where V is this E, right? And then this T is a sum over all of the particles. You can write it like this, okay? And when we are actually dealing with the dynamics of the network, yes, we will need this term, okay? So yeah, so here, if we include that, we are assuming that, so if we write the Lagrangian like this, it is assuming the system is conserved, has conservative dynamics, right? By writing a Lagrangian. Okay? And what other approximations or assumptions did we put in by writing a theory like this for a material? Yes?
That also made me feel like it would be like these symmetric interactions.
Symmetric, so this D is a symmetric matrix. And this is also related to the assumption that it's conservative, so that you are able to write a conservative energy like this. And as a result, D has to be symmetric. Okay?
There's a affine symmetry if we transform the UIs and UJs.
What is symmetry?
There's a rotational, there's a bunch of symmetries. If I transform UI with UJ, let's say by
Rotational symmetry.
or like an affine symmetry.
So if I assume this D has specific form, there would be such symmetry, right? But if I just write a generic D, that does not necessarily assume such symmetry, right? Mm-hmm. Yes? Spatial gradient terms. You mean like terms like this? Yeah. So by writing it in this discrete form, right? So we are writing a discrete elastic energy. We are assuming that we are writing it for a microscopic theory, so that you have a picture like, let me try to draw a picture somewhere. Maybe I should not connect all of the points. So just to assume there's a random network like this. Then how would such term arise? Yeah, so if you have a really large network, right, and I say I want to take the continuum limit, then the difference of displacement here will turn into a gradient term. But what we are writing here is at the level of a microscopic theory. Okay? Any other? Yes? So I assumed I'm starting from equilibrium. I'm expanding around So what does equilibrium specifically mean here? Sorry, what did you say? That's right. So we did not write, I'll just write it here. So in general, if I just say that I want to start from symmetries, I want to write elastic energy in terms of the displacements of these particles, right? I, in principle, should start from linear term, and then second order term, and then higher order terms, right? The reason I don't have linear term is, as you said, I assume I start from equilibrium. And it is worth pointing out that it's different from saying all of these springs are in rest length. The springs don't have to be in rest length, right? So you can have a network. You probably still remember it from Tom's lecture. You can have a network that has the state of self-stress. Then in this case, if these two, for example, are both longer than square root 2, then the thing is pre-stressed. Although it's pre-stressed, this term still goes away if it's in force balance. And the effect of pre-stress will show up in the dynamical matrix. Okay? Yes?
Did we assume central forces?
Yes, that's another good point. So we'll assume, I'm running out of space. I'll just number these ones. 1, 2, 3, 4. So what do you say? Central forces, okay. So what do we mean by central force?
It's a force that depends on the distance between two particles.
Yeah, the force only depends on how far this point are, right? So, or more specifically, if we have interactions that are beyond the central forces, can we still write it in that way?
They don't have to point towards, the forces don't have to point between these particles, but
Yeah. So central forces would be very natural to write it like this, right? But if you have interactions that only depend on these distances, but only depend on the displacement vectors, but it doesn't necessarily need to be pairwise central force interaction. For example, if I say I introduce an interaction that depends on this angle, I can still make an expansion and write it into that form, right? And the real assumption here is that each building block is only described by its center of mass. Okay? It can be beyond the central force interaction, but it does not describe the fact that maybe here the particle has a shape, and its orientation actually contributes to the elastic energy. And that is ignored by writing it like this. Okay? Any other points you can think of that we made assumptions? What?
We are considering infinitesimal displacement.
Infinitesimal displacement. So yes, can you imagine if the displacements are not infinitesimal, what would go wrong by writing it into that form? Yeah, you will need to include higher order terms. Right? So it's the same as assuming it's a linear theory or harmonic energy. Okay? So maybe it's useful to think in terms of like what kind of material is described by such a theory, by a Lagrangian like this. What kind of real systems can you think of? That's a very open-ended question, right? Many systems could be described approximately like this. Can you think of some examples? Fishnet. Fishnet, okay, that's an interesting one. So you mean like a woven material? I think I should not draw it disordered. Fishnet is usually ordered, right? Some kind of net like this. Just very schematically, right?
And that does not resist compression.
Right, so what is missing if we try to write such a theory for a fishnet? What would go wrong? Negative what? Are you saying that this network doesn't resist compression, right? It will buckle if you try to push it together, right? So mathematically, what does that mean? If I ask you what is wrong with this form, mathematically, what was wrong? Right, it's not a quadratic. So if some element buckles when you compress it, but resists stretching, you will have a force displacement curve that is like this, right? And a force displacement curve like this will not be described by this quadratic form. So yes. Any other examples could you think of? Spring network? So yeah, that's more like by definition, it has to work, right? Spring bead network. So even for this, can you think of a way when this does not work? What would make it not work? What? Nonlinear springs, okay. So nonlinear. What else could invalidate that Lagrangian? Non-reciprocal springs, okay. Yeah. So dissipation is an important factor that the elastic energy can still be written like this for a spring network. But when you actually excite it dynamically, it's not totally governed by this Lagrangian. Some energy will be dissipated, okay? Any other? We'll just do one more as a little practice. With what? Ah, okay. Atomic crystal lattice. So it's an interesting point. So this type of description initially comes from when people try to write elasticity for crystals, right? You start from some true, more complex, like quantum mechanical interactions. And then you say that for the limit of small displacements, you can expand the energy of the system in leading order, then you get a theory like this, right? Then when you try to apply this theory to atomic, atomic crystals, what would be missing? Quantum. Yeah, so we are not doing anything quantum, right? So what are the quantum effects that would have been included if we have a better theory?
And probabilistic precision.
Yeah, so there will be, so I think both quantum fluctuations and the thermal fluctuations would tell you that the particles are not frozen in space, right? They will be fluctuating around. And if it is a thermal system, you could write an effective theory. So there are many ways to do it. You could start from real energy, and then you say that there are small fluctuations, and then you integrate out the fluctuations. You correct the leading order theory, right? And similarly, you can do that for quantum fluctuations. And another effect that you probably remember from solid-state physics is that the statistical mechanics is different. Right? So if you have a purely classical system, all of the modes are excited by equipartition. But if it's a truly quantum mechanical system, each of the modes should be treated as a harmonic oscillator. And there will be quantum fluctuations that dominates low energy theory. Okay? But we're not going to go into too much detail there. So this is just to serve as a starting exercise to help us think more broadly. When we write a theory, simplified theory like that, what are the approximations we are making? And if we want to improve that theory, what are the things we should add? Or what are the new ingredients we could add to make a new theory, right? Okay, so that's the first part. And next, I would like to do another, just a small exercise. Let's think about a game, right? A game one. If only particles are visible, the springs are not visible. And I can do some experiments on the system, and I try to figure out which particles and which particles are connected. What can I do? So what I can do is to give prescribed forces to particles and observe displacements of all of the particles. I want to know what is the network connectivity. What measurement should I do to figure that out? Or I want to know what is my dynamical matrix. Vibration. So how do you do that? You shake some sites, right? So you, for example, you give some site a force with some frequency, right? And I observe the reaction of the system. So mathematically, how do I describe that? Or how do I describe an even simpler question? If this is a constant force, how is it related to the displacement?
For normal modes?
Yeah, so that answer comes from that form, right? So you just use this matrix, right? And if you have prescribed force and you want to know what is U, you inverse this matrix. And by repeating this enough times, you get all of the entries of this matrix. Okay? So this is just a way to think about how do we extract information of a system that you only have partial visibility, right? This comes up a lot in experiment. So sometimes imagine you have a colloidal scale system. You have colloidal particles, and you know there are some interactions between them, but you don't know what the interactions are. You can do this type of observations. And then let's consider another game. I cannot assign forces. I can only observe. But the system is in thermodynamic equilibrium. At temperature T, how do I figure out what are the interactions between the particles? With correlation functions, right? So what should be the form of the correlation functions? I will clean up some space over there. So firstly, what are the correlation functions? How do we define the correlations? So yeah, displacement correlation. So if I just generically write it like this, what is the average here? The thermodynamic average, right? And how should this relate to the theory that I have elastic energy like this? Mm-hmm. Yeah. So in general, you can calculate this using equilibrium ensemble, right? So I just write it like this. You integrate over all of the possible configurations of the system. And because this is a Gaussian integral, if we keep to only harmonic order, this would just become okay. And then this offers you a way that by measuring such correlations, you will learn about the interactions, right? So this was actually a method that has been used in a paper from Andrea Liu and Adrian Yudo's group several years ago. They observed colloidal glasses. In principle, we don't know the details of the interactions between the colloidal particles. But by looking at a video of the colloidal glass, you can track the particles and do this kind of average correlation function. And then using that, you can back out the interactions between the particles. And we have also been using this for nanoparticles to learn about macroscopic interactions. It can actually tell us a lot. Okay? So these are just some examples to get us started. Any questions about any of the questions we talked about here? Yes?
Connectivity, because you said you couldn't see the connections. We use
Yeah.
Voronoi diagram.
So, right. By doing this, I do not need to know who is connected to who, right? So by looking at this correlation function, I measure, if I define Cij to be Uiuj, then D is supposed to be, let me see, 1 over kBt C inverse Ij, right? I just take this high-dimensional real space correlation function matrix, and I do its inverse. If the data is perfect, I will see only entries of the particles that are interacting with one another. So I should get a symmetric matrix, real symmetric matrix, where I only have entries of, so this is the D, okay? I only have entries of the particles that are connected to one another, right? There will always be diagonal entries. And the others should be 0. However, in real experiment, other entries may light up a little bit too. But with certain cleaning, you should be able to filter and get the interactions. Okay? You had a question?
Yeah, if you have perfect data is the key there.
Yeah, that's right.
If you got a big matrix, getting an inverse requires high precision.
That's right.
Of certain entries. And yeah, so in practice, you get an approximation.
Yeah, that's right. Thank you. Yeah, and this method, you can work with it in many different ways. So we have used it on periodic lattices. If you have a periodic lattice, then you already know that D block diagonalize into different momentum components. Then for each momentum component, you just have a small matrix that is much easier to fit. If it is a large random matrix, yeah, that is going to be difficult, and you need a huge amount of data to do that. Okay. Any more questions? Okay, so next I would like to talk a little bit about dynamics, and then get into the discussion of rheology a little bit. So if I want to write a generic dynamic response, let's start from the equation of motion, right? Which I think you all know how to write. Okay, so I just write an equation of motion where I have the elastic response of the network. And this is some external force, which can be added on arbitrary number of the particles in the network. Right? And this is some dissipation term. Okay? And then suppose I would like to solve this equation and find the dynamical response of any form of external perturbation. I want to know how the system responds. What is the procedure to solve the problem? I believe you have seen this type of problems, right? So basically, it is much easier to go to frequency space instead of doing the differential equation. So you decompose into Fourier modes. And because different frequency components are orthogonal to one another, I can just turn this equation into an algebraic equation in frequency space, right? So I will just have then I can formally solve it, right? By writing ui omega equal to okay? Is it clear what this means? Okay. And what is this called? It is a Green's function, right? It is elasticity. Was there another? Or susceptibility? Okay. I think there are different names, right? Okay, and we can call it G of omega. But still, it is an inverse of a matrix, right? How do we get the useful information out of it and analyze the actual dynamics of the system? Yeah, you need the eigenmodes, right? This is where the eigenmodes of the dynamical matrix becomes really useful. In particular, I suppose D can be diagonalized. So this is the diagonal matrix of the eigenvalues of the dynamical matrix. And these V are matrices made of the eigenvectors, right? These are all eigenvectors of D, okay? And so here, what kind of matrix is D? What is the property of this matrix D? It's a symmetric matrix, right? So it's a symmetric in real space. If I write it into Q space for lattices, what kind of matrix it is D? if it is, I write it into dq. It's Hermitian, yes, that's right. Now, what kind of matrix is V? It's orthogonal if I do it in real space, right? V is orthogonal. And V of Q, if I do it in momentum space, what matrix is V? It's a unitary matrix, right? Okay, so it's just like a review some basics to remind you of how this method goes together. Okay, so now with this decomposition, we can have a full answer to this time-dependent dynamics question, right? We have now U, I of omega. I can write this D as its eigenmode decomposition, right? And then there are different ways to write it. Using Brand Kit, you can write it in a compact way like this, right? So what do we learn from this answer, right? What this tells you is that if you have a frequency-dependent perturbation where you can act that on multiple sites on the lattice, and I ask what is the frequency-dependent response, I can write it in this form. Right? What is this part of my answer? Yes, it projects the external force onto a normal mode, alpha. So alpha is a sum over normal modes. And the modes are the eigenvectors of the D matrix, right? I project this F into each mode. And what is this denominator? Or say, what is 1 over this? There are different ways to call it. Sometimes it's called a propagator of mode alpha. Okay? So what it tells you is that this is the amplitude of how much that external force projected to a mode. And this is going to be how sensitive the system is, how sensitive that mode is with this particular frequency of perturbation. Okay? And then after you multiply this projection and this propagator, you project it back into real space. Okay? So that is the full answer of how, so this is basically how strongly each of the normal mode is excited when you have these external forces. And then you translate it back to real space on each site. Okay? Any questions? So this is now in frequency space, right? What happens if I try to write this in real space, in time domain? This is in frequency domain. So if I define this to be chi of mode alpha, right? You know that in frequency space, it's UI. Let me just rewrite it here. Okay. As you can see, this is a product in frequency space, right? You take the product of f in frequency space and the chi in frequency space. If I Fourier transform it back to time domain, what should I get? Ui of t. It should become a convolution, right? So I still sum over all of the modes. Okay? Now this is a form which looks sort of easier to interpret, right? I have a time-dependent perturbation, not a perturbation. This is actually full scale. So I have a time-dependent external force that act on the network. And the dynamics at a point, at a time t, at a site I, actually is an integrated result of the whole history, right? So I need to integrate from minus infinity to positive infinity. And then I see some of you look confused, right? It should not depend on what happens in the future, right? How is that taken care of? Yes? Yeah, so chi has to satisfy causality. So in fact, if you take this form and do Fourier transform, you will see that the function will be 0 here. And then with some, it depends on whether it's overdamped or underdamped, you will have some, I don't know what the form it is, I have to calculate it. Something like this. It is all taken care of by this sign here. Okay? It's because it is a retarded Green's function. So what other properties can we learn here? When we write the dynamical response of the system like this, or any questions? What do we learn when we write it like this? Or maybe I can ask you a question, right? So firstly, what if the external force is something like this? I just give it a monochromatic force. I just give it one frequency. And this omega naught happens to be one of the eigenmode in the system. Happens to overlap with an eigenmode. What will happen?
Resonance.
Yes, you get a resonance, right? And what controls exactly how the system responds when it hits resonance? Does it diverge?
There's damping, if you have damping, it does it better.
Yeah, so if I have a finite eta, then it doesn't diverge, right? So you should have, you can write the real and the imaginary part of this response function, and it's something like this. This is the real part. It is an even function as a function of omega. And then you have the imaginary part. This is chi double prime, which is an odd function. Okay? So what is the physical meaning of the real and the imaginary part of this response function? Or in particular, what does the imaginary part tell us? It is the dissipation, right? So for example, you can ask, so we're supposed to go to 4, right? 4. Okay, yeah, I think we have, we're on track. So let me see. I don't want to go into too much detail of the linear response, but we'll just do the main steps here. So if I have such a single frequency force, I can write it in frequency space. This is just the Fourier transform of that force, okay? And then you have ui omega. You can plug in that form, which I'm not going to write. And you can write ui of t. With a little bit of simplification, you will find it like this. This is at each site. Okay? So this is just a few lines of math when you write the frequency space and do the Fourier transform, because chi prime is symmetric and chi double prime is chi prime is an even function, chi double prime is an odd function. The integral has terms survive like this. Okay? And then you can already see the external force, F external, is proportional to cosine omega naught t, right? What conclusion do we get here? What does chi prime and chi double prime tell us in terms of the response of the system to a frequency, to a perturbation with a frequency? Yes? Yeah, so this is the in phase. And this is the out of phase. And there is another way to rewrite it which is to combine these two using formula of trigonometry. I think you have all seen. We can write it as this whole thing. Where tangent of delta okay? And then now you can see very clearly that this delta is a phase lag, right? The force you give the system is cosine omega t, but the response of the system can be written as the signal delayed a little bit in time, right? So schematically, you can write the external forces like this. But the displacement is something like this, where this is delta. The more larger the imaginary part is, the more delay it is, okay? And in fact, if you calculate the dissipated energy, you will see that dissipation is only controlled by the imaginary part. Okay? Any questions? Yes?
What happens if I take eta tends to 0 at the limit here? I would expect the UIDs to blow up.
Yes, that's right. So you're saying if eta goes to 0, right? And then this function, this will become a true delta function, right? And the real part will become delta prime. And you get exact resonance. Usually when you have a little bit of dissipation, that broadens the peak. Is that what you're asking? Okay. Any other questions? Okay, so this is like, so far what we talked about all are microscopic theory, right? Microscopic theory, where we assume there is some kind of microscopic level network, and we ask if there is a time-dependent force on it, what is the response? And the calculation here tells us that if you know all of the eigenmodes, you can exactly calculate it. The eigenmodes provide you with a really convenient tool. You project the perturbation to all of the modes, and each of them respond in a simple way. And then, because it's a linear problem, you just add up the contribution of all of the modes, right? And now let's, with the rest of the time, let's think about a more complex question, which is the rheology of real materials. So I don't know, how many of you are familiar with rheology, or has ever, some of you, or how many of you have ever touched a rheometer? Oh, some of you, that's great. Okay, so this is not like only theorists, right? So For those of you not familiar with it, rheology is basically a branch of soft matter experimental methods that has to do with flow and deformation of matter. It's basically how materials flow or deform under external drive. And there are many different types of rheometers. Rheometers are this basically a device that help you study rheology. And as a theorist, I'll just give you a cartoonish picture, right? So basically, you can imagine you have a cylinder. And it's a container, basically. And you fill your soft material inside of this cylinder. And then you hold the bottom and try to rotate the top at a certain frequency, say omega. And you see how the system responds. And more particularly, you measure the relation between stress and strain. So are you all familiar with what are stress and strain from Tom's lecture? So just to refresh a little bit, strain describes the deformation, right? It's a second rank tensor, epsilon ij. So which you imagine you have a material under certain type of deformation, each of the mass point R goes to capital R, right? And you can define this tensor that measures the gradient of such a deformation. And by combining it like this, the after deformation vectors contract with one another. And all of the subindices have to do in this space. So it is a tensor in this space. Okay? It describes how much the system is deformed. And the stress describes internal forces. And you probably heard that there are many different versions of stress, Cauchy stress and Kirchhoff-Piola stress. And I don't want to go into the details of the difference. The stress basically means that if I cut a little interface in the material, what is the mutual force that this part of the material gave this part, this material gave this part. And it is also a tensor because you have a normal to this interface, and then there is another direction of the force. So both of these are rank 2 tensors. Okay? And what, in general, a rheometer measures is the relation between stress and strain. And in the simplest limit, if you're not familiar with this description, you can think of this as Hooke's law, force with displacement. Okay? Any questions? So in general, we are often interested in rheology of disordered materials, right? Such as a polymer network or a colloidal glass. And in general, the response can be called viscoelastic. So what is viscoelastic? we know what is elastic, right? If a material is elastic, what is the relation between stress and strain? It is proportional, right? So you have stress and this is your elastic constant matrix. And if we just talk about the very simple limit, Cartonish limit, we just write a Hookean's law like this, okay? For a viscous fluid, what is the relation between stress and strain? What did you say? Is the what?
The time derivative of the strain.
Sorry, I still have a number.
The time derivative.
Time derivative, yes. So for a viscous fluid, in general, you have this. So the stress is proportional to strain rate instead of strain. And viscoelastic is, in general, something in between. You have, the system has this behavior and this behavior, but it can show up in many different ways. And a group of models that people often use phenomenologically to describe viscoelasticity is so-called the standard linear solid. So which is basically just to treat the real material as a circuit. You just, for an elastic element, I can think of it as a spring like this. For a viscous element, I think of it as a dashpot like this, so-called a dashpot. This is a spring. And the real material, you just think of it as certain combination of springs and dashpots. The simplest models, I forgot the name. I think there are Maxwell linear solid model and other versions. For example, you can have something like this. Or you can have something like this. What would be the difference between this type of system and this type of system? Just intuitively. So this element only cares about how fast you pull. And if you stop, eventually it should go down to 0, right? And this is just a normal linear spring. And you can also make more complex versions. Right? So firstly, what would be an obvious difference between this case and this case? At 0 frequency, right? So at 0 frequency, what would be happening for this one? There would be no stress because the dashpot will accommodate whatever constant strain that is left. But here you will still have a stress left, okay? And in general, for this kind of combination, you can always write the combined elastic modular. For example, for this one, if I call this E1, this E2, just like what you do for electric circuits, right? This would be, sorry. E2 plus okay? You have these two in series, so you get this part, and this in what is called parallel, you get the sum, okay? And you can do it like this. So now let's, with the last 15 minutes or so, let's think about how this relates to all of the microscopic model we talked about so far. This is phenomenological level of description. Right? What do we mean by phenomenological theory? And this is a microscopic theory, right? What is the, so in physics, when we say some theory is phenomenological, some theory is microscopic, what do we mean?
Based on observations and based on first principles.
Yes, that's precisely. So phenomenological means that I treat the system as a black box. Sometimes I just think about symmetries, broken symmetries, and I start from that and write a theory. And the microscopic theory means that you actually think about what are the interactions, what are the building blocks, and try to start from that and build up the length scales. Now we have this phenomenological theory. We just guess there is some kind of viscous elements in there, elastic elements in there, and they play together to determine what you see. And then on the other hand, we can start from macroscopic theory, right? And what we can do is then to compare the two sides and then say, these parameters here actually come from the macroscopic theory in some way, okay? So how do we actually relate them? So let's try to use the results that we just described today, right? We say that when you give some kind of perturbation to a system, let me just draw the network again, just some random elastic network like this. And imagine this is in a rheometer, and I try to predict what its time-dependent response. Then it is like you really need a large-scale model, and then you say that some of the sites are actually glued to the top, and those are the ones that actually grab and rotate, right? You could do it in that way, computationally. Here, we will just do a very simple cartoonish model again. I just say that I grab one point and give it a time-dependent external force, okay? Then the effective Young's modulus, if I want to compare it to this quantity, is what kind of ratio on this network? What would be qualitatively the same as taking the ratio of, so this is taking the ratio of stress and strain. Yeah, so it's qualitatively the ratio between this external force and the displacement of this site, if I just call this site I, right? It is roughly something like this. Does that make sense? So imagine this is what I control, right? I just grab this one and shake it at a certain frequency. And I ask how large is the response of that site. I take a ratio. It is roughly the elastic module I am looking for, right? Then what goes into this? How does this ratio depend on, for example, the dynamical matrix of this network? It is, again, the whole thing we did, right? We can just plug in this formula again. Okay? And then if there is only one site that is being shaken, these two just cancel out, right? It's just one force. And then what you get is, basically, remember, this quantity is just that response function, right? What you get is roughly the response function of each of the mode added up and then take inverse. Here I ignored the projection into the modes. It actually should go into the prefactor here. But basically, the effective elastic moduli in this simple thought experiment comes from the contribution of all of the modes added up. Okay? Yes?
First order in
First order.
displacements from, for example.
Yes. Yeah, so we consider the elastic energy to be like this. So with a force, you'll get a linear response. Okay? Any questions? So this is mostly, I think, what I would like to talk about. And I think next I would just to start a little bit of open-ended discussion from this result and try to see what we learned, right? Yes? Oh, so if you only grab one site and shake it, that's only one term here. So let me write it more specifically. So this Fj would be Fi delta ij, right? So then this would become okay? Yes, and this I is not a summed over. I know when I write it like this, it's a little bit confusing. Actually, yeah, this I is the site. I gave it the force. And then when, no, I think that is just the form. Okay, there, I don't see any further simplification. Any other questions? Yes? That's an interesting question. So if I write it out, this chi is this. I think you can write it more cleanly with dynamical matrix. This is just to make it more explicit. Each of the mode reacts with its own response function. Yeah. You can write it as, I think, because this is, if you want to write it in terms of dynamical matrix, this is it's actually not obvious it's simpler because I do not know the displacements of everyone else. You cannot write like F is du, right? If you know the displacement of all of the other sides, you can do it like this. But I think this should be simpler, right? Any more questions? So I just want to add a little more comments. So firstly, here, we just keep it generic and have this inertia term. For most soft matter systems, this can be dropped because we work in overdamped limit, so you actually only have this term. That's one thing. And the other is obviously these should be tensors and treated more carefully. Here, I'm just giving you an intuitive picture. And I think here is also maybe helpful to relate a little bit more to disordered networks, since I think we have a few more minutes. And just let me know if you have questions. So suppose you have a disordered mechanical network. Qualitatively, what do you expect the frequency-dependent elastic modulus to be? At a very high frequency, what should we see? If you shake a network really, really fast, faster than all of the eigenmodes, it
Low energy, low total. Oh. You should expect a bell like.
it's confusing, right? So I think because there is one step I didn't do carefully here, which is the dissipation term. So where is the? I write the equation of motion into something like this. Okay. And imagine you actually measure the property of the material in a rheometer. This term actually need to be treated more carefully because there is a fluid. The network is immersed in some fluid. And the fluid is actually moving affinely in the rheometer. So this should really be more carefully written as U minus U affine response. Affine response, I think maybe Fred talked about, means that it's a homogeneous strain. And a disordered network, in general, if you shake it at 0 frequency, if I now talk about omega equal to 0 limit, what should be the response? It's in general non-affine, right? And if it is a solid, if it actually has a non-zero low frequency plateau, you should see something like this. Right? It goes to some finite value. And this is the fully non-affine elastic modulus. Then what happens at a very high frequency? By looking at the computation between these terms, you would see that this term would drag the network to just move affinely with the fluid. Right? And you will typically get a plateau here, which means the whole thing cannot adopt the lowest elastic energy deformation. It has to move so fast that it just adopts whatever the solvent is behaving. And then there is a crossover from the non-affine to the affine behavior. This is typically the real part. And what happens to the imaginary part? So in this limit, it doesn't dissipate very much, right? You move the system at a very low frequency. And how about this limit?
This is very dissipative opposite, right?
Dissipative. Actually, I'm a little confused myself. Should it be like a peak here, or it keeps going up? I think maybe.
Well, if it's the network, then typically you've got a solvent there as well, which is what's coupled
Okay.
through your, and so in general, at high frequency, it always takes off.
Always goes
solvent,
up.
which is
Okay.
accounting for most of the stress. But yeah, there would be an underlying network part.
Okay. So this is the network contribution. Okay?
With any polymer network, both G prime and double prime,
Yes.
typically continue off to infinity control.
So this will keep growing, right? Yes, thank you. Any more questions? I think we are almost at the end. Yes? Yes.
Could you explain the notion why it arrives at a plateau?
Oh, why the real part goes to a plateau?
Yeah.
So if everything moves finely, you have a limit, right? You have a limit of how much elastic energy is going to cost. It will not keep increasing. This is a real part. Is that what you are asking?
The real part is not so different from a single damped spring, where if I drive a single damped spring at a certain frequency, pull the frequency up.
A single, so if you have a single damped spring, you will not have this crossover, right? This crossover, I think, qualitatively, you could think of it as, if you want to match it to linear elastic solid, standard linear solid, it's something like this. So this type of model exactly have that behavior. So at low frequency, it is, at a very low frequency, it is the, you get E2. At high frequency, you get E1 plus E2. Yeah, that's right. Okay. The real part. Okay. Okay, any other questions? So I didn't explicitly list any references. I have a reference list I'm going to send it to Danilo, and he will forward. Like, it will have the background and give credits to the papers where I learned this from. Okay? Okay, thank you very much. See you tomorrow.
Okay, thank you, Xiaoming. We have coffee break, and we'll come back at 4:30 for the exercise session. Okay.